everyone. I am Dr.J Suresh Goud, Associate Professor in Department of Mathematics, Institute of Aeronautical Engineering. Today, we are going to discuss about Poisson distribution. Before going to discuss about this topic, we have to discuss binomial distribution that we have discussed earlier in the previous sessions. What is binomial distribution? What is the use of binomial distribution? Binomial distribution is denoted by b of x comma n comma p. And to find probability of getting number of successes by using the formula NCX p power x q power n minus x. This x is varies from 0 to n. This we have discussed in the previous session. Now, the Poisson distribution also can be obtained by binomial distribution only, but under the following three conditions. If n tends to very large, in case the number of trials are very large, and p tends to very small, that means the probability of success in a single trial is reaches to 0, not exactly 0, up to 0. And if you multiply n and p equal to lambda, under these three conditions, already we discussed binomial distribution converts into Poisson distribution. How it is? See, b of x comma n comma p, this is called binomial distribution, tends to Poisson distribution under the following conditions. That is, n tends to infinity, and the second condition, p tends to 0, and third condition, n into p equal to some constant value lambda. The binomial distribution converts into Poisson distribution. This is the symbol of Poisson distribution. And this is also to find probability of getting number of successes only by using the formula e power minus lambda into lambda power x by x factorial. But in this case, x varies from 0 to infinity, not 0 to n. Got my point? The Poisson distribution can be obtained from binomial distribution only under the three conditions, which are n tends to infinity. N tends to infinity means n is very large. That means the number of trials are more. We cannot use binomial distribution. And p tends to 0. P is very small. That means the probability of success in a single trial is very lowest value. Also, we cannot use binomial distribution. And if n and p, if you multiply, we'll get some constant value lambda. Under these three conditions, binomial distribution converts into Poisson distribution. And this is the formula of Poisson distribution. F of x comma lambda equal to p of capital X equal to small x equal to e power minus lambda into lambda power x by x factorial. How we got? By using these three conditions, we have a theorem. That is, the Poisson distribution is a limiting case of binomial distribution. This is very important theorem. How we are going to get Poisson distribution from binomial distribution, we are going to explain in this theorem. See, the definition of binomial distribution, we know that. Formula is NCX p power x q power n minus x. We are going to apply three conditions on binomial distribution. What is the three conditions? N tends to infinity, p tends to 0, and np equal to lambda. See, this is the binomial distribution NCX p power x q power n minus x. First, replace NCX formula. NCX equal to n factorial by n minus x factorial into x factorial. P power x into q power n minus x. Actually, what we need to get? E power minus lambda, lambda power x by x factorial. From where? NCX p power x q power n minus x. From that case too, we need to get this value. How we will see? First, NCX formula we have written. N factorial means we can write as n into n minus 1, n minus 2 and so on, up to n minus x factorial you write. If you write n minus x factorial, the previous term is n minus of x minus 1 by n minus x factorial into x factorial p power x into q power n minus x. So n minus x factorial, n minus x factorial cancel. So the remaining terms are n into n minus 1, n minus 2 up to n minus of x minus 1 by x factorial p power x into q power n minus x. Now, the third condition you take under the following conditions I told you na. In that conditions, third condition np equal to lambda you take. From this we can write as p equal to lambda by n, q equal to 1 minus lambda by n because p plus q equal to 1. This p value, q value you substitute in the 1. What happened? N into n minus 1, n minus 2 up to n minus x minus 1 by x factorial. We have p. In the place of p, you replace lambda by n whole power x. Q. In the place of q, 1 minus lambda by n whole power n minus x. Okay. From this x factorial and this lambda power x we can take outside. Lambda power x by x factorial. Actually, what we require e power minus lambda into lambda power x by x factorial. So already you got it. Lambda power x by x factorial we got it. So remaining you simplify it for the value of e power minus lambda. See, 1 by lambda power x we have taken outside. This n power x I written here and 1 minus lambda by n whole power n minus x. If you observe in the numerator we have 1, 2, 3 up to n minus x minus 1. From here to x minus 1. How many terms are there? X minus 1 terms are there. Including these terms, how many terms are there? X terms are there. Numerator we have x terms are there. Denominator we have n power x. N power x means n is in terms of x times. You can separate each term. N by n, one term. N minus 1 by n. Second term, n minus 2 by n. Third term, last term, n minus x minus 1 by n. Like that, we have x terms. Because in the numerator also x terms. Denominator also n into n up to x terms. That can be written as n power x. And this is as usually we have written. N by n, 1. N minus 1 by n, 1 minus 1 by n. N minus 2 by n. Like that, we can simplify it. And n by x, we can write as numerator n by denominator x. So up to here we got it by applying np equal to lambda. And the second condition you apply n tends to infinity for the above equation. You apply limit n tends to infinity lambda power x by x factorial remaining as usually we have written. This lambda power x by x factorial you can take it outside because there is no expansion for limit n tends to infinity. And 1 minus 1 by n tends to 0. Infinity means 1 by n tends to 0. 2 by n tends to also 0. 3 by n tends to also 0. Like that x minus 1 by n tends to also 0. 1 minus 0 into 1 minus 0 into 1 minus 0 and so on 1 minus 0. It will be 1. And here also lambda by n tends to 0. This one also 1. Except this term, the remaining all are 1. So that point I have written here. Limit n tends to infinity. 1 minus lambda by n whole power n. This is we are going to simplify. See here what we have done. Here we have one formula in intermediate level. Limit n tends to infinity. 1 plus x whole power 1 by x equal to e. So it is 1 plus x whole power 1 by x is not there. To get 1 by x you can multiply with reverse minus lambda. Multiply and divide with minus lambda. Now this is in the form of limit n tends to infinity 1 plus x by 1 by x, e power minus lambda. So we got it. Therefore, f of x comma lambda equal to probability of getting number of successes equal to e power minus lambda, lambda power x by x factorial. So this is the Poisson distribution. How we got this Poisson distribution? From binomial distribution only by applying the three conditions. But here we are getting one doubt. Sir, we applied only two conditions. NP equal to lambda and n tends to infinity. But we did not apply p tends to 0 condition. No problem, because NP equal to lambda means p tends to 0 condition is applied. That's why no need to apply this condition. Okay. So finally we got it. B of x comma n comma p equal to p of x equal to x equal to ncx p power x q power n minus x for all x equal to 0, 1 to n. This will be converted into Poisson distribution f of x comma lambda to find out same probability of getting number of successes by using the formula e power minus lambda by lambda power x by x factorial. But here for all x equal to up to infinity, because we applied n tends to infinity. Okay, so that is the limiting case of Poisson distribution. Poisson distribution is how we are going to get the Poisson distribution? Poisson distribution is a limiting case of binomial distribution. We are going to get the Poisson distribution from binomial distribution only. Now, the total probability in Poisson distribution is unity, like binomial distribution also. In binomial distribution also, we discussed the same concept. The total probability in a binomial distribution is unity, we proved. Now, for the Poisson distribution also, we are going to prove the total probability should be 1. See, by the definition of Poisson distribution, now we are going to prove that total probability. Total probability means summation you did, some sigma x equal to 0 to infinity you take, because in Poisson distribution x 0 to infinity. E power minus lambda, lambda power x by x factorial. Here e power minus lambda we can take outside, because there is no effect of e power minus lambda if you take sigma x equal to 0 to infinity. Because the summation is from x 0 to infinity. There is no effect for e power minus lambda. Lambda power x by x factorial. You put x equal to 0 in the first step. 1 by 0 factorial. X equal to 1. Lambda by 1 factorial, x equal to 2, lambda square by 2 factorial, and so on. So, e power minus lambda into will get 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus lambda cube by 3 factorial, and so on. But in intermediate, we have one formula, 1 plus x square by 2 factorial, x cube by 3 factorial, and so on is e power x. But instead of x, we have lambda. That's why e power lambda. So, e power minus lambda into e power lambda equal to 1. Therefore, the total probability in a binomial distribution is unity. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.